Xin chào tất cả mọi người. Good morning everyone and welcome back to ACL Technology Vietnam TikTok series. So thank you for your present in today's the virtual session, Semiconductor Capital Equipment. So today is another beautiful Saturday morning is here. So one of the days when there is no rush for anything and one can stay in bed a little longer. But you are here with us, appreciate that. So my name is 𝗦𝗲𝗺𝗺, Senior Marketing and I'm your host. But now we are waiting for more people to join.
In July 2020, HCL began its journey in Vietnam. It was also the same period when the dreadful pandemic pushed the whole world behind closed doors. But technology came to the rescue and the world remained connected. Thus, in order to ensure regular dialogue, free flow of knowledge, thoughts and ideas, HCL Vietnam Tech Talk series was envisaged. In this HCL Tech Talk series, HCL experts share ideas on technology, future of workplace, connected living, and connected enterprise. The series went live on December 2020, and since then, sessions on various high-tech technologies such as machine learning, artificial intelligence, Internet of Things, digital manufacturing, cybersecurity, etc. have been conducted. HCL Vietnam is committed to shape the technology of the next decade today. HCL Tech Talks will keep bringing many such valuable tech talks to your home screen. Stay tuned.
Welcome back. I know a lot of you here have attended our webinars before and surely you already know about us. But for people who are newcomers, I'm gonna show you more about ACL Technology Vietnam. So as you can see, ACL Vietnam has started over years ago and as on date, we are located in two locations, Hanoi and Ho Chi Minh City. We are serving 30 plus global customers from both locations with a diversity ratio of 27%. ACL had also successfully set up a university partnership program where we have got over 15 universities. Our focus area for Vietnam is the high-tech areas, which also include digital transformations and a key focus area for us. And the domain where ACL Vietnam is focusing on from banking, insurance, other financial services, automobile and manufacturing, pharmaceutical, medical device, CPG, and retail. We recruit people who are experienced professionals in Vietnam. We also look at fresh university graduation and also students who are all undergoing their university education in the 7th and 8th semester. In the next 3 years, ACL Vietnam is poised to grow to strength of 3,000 employees to provide services to clients in various high-tech and cutting-edge technology. If you have interested in career opportunities at ACL, please visit our website aclvietnam.com and follow our fan page to find out available jobs. A 10-hour visual session today, we have Mr. 𝗦𝗃𝗺𝗺 Panduragan, General Manager, the Library Head of ACL Technologies, to share the updates on semi-equipment. I'd like to introduce more about today's presenter. 𝗦𝗃𝗺 is a mechanical engineer with 20 years of experience and 80 years with ACL in semiconductor capital equipment, based in Chennai, India. He spent 7 years in the US at customer locations, Boston, San Diego, Silicon Valley, responsible for mechanical engineering design, precision energy engineering, digital documentation, and AR/VR. So, and you may send in your question at any time during the presentations. We will collect these and address them during the Q&A session at the end of today's presentation. For those of you just joining us, welcome. To begin, I would like to invite Mr. Dana. Hi, Dana. Hi, Dana.
Hello, Mike. Good morning.
Yeah.
Can you hear me well?
Yes. So I really appreciate your time today. So please help us to know more about semiconductor capital equipment, please.
Sure. Okay. All right. Good morning, everybody, especially from the location of Vietnam. I'm very happy to give this session on behalf of HCL team. Today, we are going to talk about a quick introduction about semiconductor capital equipments. So why it is so important, and I'll give a insight and what is the emphasis on the precision engineering and the future of semiconductor. Before getting to the next slide, I will give a quick introduction about me. Maya already explained about a few informations about me. People call me Dana. I've been with HCL for 18 years, and almost 17 years I've been working with semiconductor equipments customers. So this is one of the fascinating field, and I've been continuing in the same. When I spent a lot of time in the US, close to 7 years, I really had an opportunity to learn the nitty-gritty and the insight of semiconductor equipments, why it is so called high tech, and what is so important about this industry. As we move forward, I will share some of my experiences. Okay, so with that, I'll move on to the next slide. So today's objective, so I wanted to, instead of agenda, I wanted to give a few bullet points at the end of the 1 hour presentation. So what are we going to learn, or what are we going to understand? So there are a few points I wanted to emphasize. One is, I will give a background on basics of semiconductor industry and the chip design. So since it is an introduction session, so I'm not going to do a deep dive. It may not be the right way to do. So I'm going one step at a time. So then the second point, I will talk more on semiconductor process flow, so which includes design, fabrication, packaging, then test and finished goods. So then the other one is we will put more focus on capital equipment. So what is this equipment all about? What does it do in the entire chip design? Why it is so important. Then I will also touch upon the future of semiconductor industry and some of the technology advancements, what we are foreseeing. Then we will conclude with some of the fascinating career opportunities in semiconductor capital equipments, and if you want to build, what are all the skill set you need and how the career path would go, followed by question and answer. Okay, moving on to next slide. So this is a big picture about the semiconductor industry. So because now in last 2 years during the pandemic, every time people talk about any delay on the sensors, people say, hey, because of semiconductor delay, right? So is it really a big industry, right? That is what I wanted to cover first. The answer is yes. So this is one of the huge industries across the globe, and if I wanted to quantify it, it is $500 billion market. So any device you take, any electronic gadgets you say, there is an semiconductor device on it. So you take a car, there is a sensor. You take a airplane, it is series of sensors. You take a F1 Formula One car, you have. So you name it, there is a presence of semiconductor devices, right? So it makes sense that this market is growing, and it has already grown up to a greater extent. And this 500 billion, includes 100 billion business from semiconductor equipments. It is, I can say, it is one pie of the entire semiconductor spectrum, right? So what is this semiconductor industry? Who are all the major players? So if I say that any company who does either design of circuits or fabrication of devices or integration of devices or testing on these devices, they're all part of semiconductor industry, right? So mainly what they do, right? So IC, we call it as an integrated circuits, like a transistor, diodes, RAM, etc. Then this industry has a bigger market, and this equipments and the entire design is very complex and precision in nature. They are almost at the atom level, so we call it as a nanotechnology level, and a lot of niche skill required. So I've given some of them, like a vacuum design, optical design. It uses a lot of lasers, electrons, X-rays, etc. So in short, it is very high complex, high precision field. Then where are these markets, right? So where the consumers or the manufacturers of these things? So mainly in the Southeast Asia, Taiwan and Korea side, then US and China, followed by Japan. So these are the places uh, most of the fabrication of these chips happening. Then there is a market segment. So they call, there are three major classifications. So one is called the foundry, which I'll talk in a minute. Then there is another one called memory. Then another one is called logic. Right. So in short, it is a big industry, and there are a lot of things happening, and only very few players in the world who can do this, and there is a high visibility for end customers. Right. With that, I'll move on to the next section. That is, I'll give some technical details about this industry and the players. So first one is called IDM. They call it as an integrated device manufacturer. So what it means? So they design, they manufacture, and they sell their own devices. Say, I can say Intel, i7 processor. Right? So Intel designs the circuit, how the design should be, the architecture. Then they manufacture using their own fabrication place. Then they sell on their own. Right? Same holds good with the Samsung. You take an Exynos processor, or you take any other devices, they do everything on their own. Then the second one is called a fabless, which means they don't have the manufacturing facility. They take care of only the design and the sales. I have given some of the company names there: NVIDIA, Qualcomm, Broadcom. So what they do, they give the manufacturing phase to the other place, which is called as foundry. So foundry is all about a manufacturing unit. So there is a huge setup where, if Broadcom gives their design, so these foundries such as TSMC is a Taiwan Semiconductor Manufacturing Corporation and Global Foundries, they take their input and they manufacture and give the product back to those fabless companies. Right? So foundries can operate for any customers in the world. So if you take TSMC, they may work for Samsung, or they work for any companies in the world. With their own IP secured. Right? Then the last two things on the market segment. So if we say logic devices, if I say memory devices, what does it really means? Right? So logic is all the microprocessors, basically. So like we call it as a CMOS, MOSFET, FinFET, etc. Then the memory, it is very common now. So you open your computer, you'd see all this. Memory devices, right? RAM, then the flash devices, then solid state devices like hard drives, all those things are part of memory. So I've given this background because it is easy and this is essential to understand when we get into the semiconductor industry. Okay, with that, I'll move on to the next slide. I have given some closer insight, why high precision required. Now, I have mentioned in the previous slide, when you compare with automotive or aerospace, why this has more precision. This is the very simple reason is now they're dealing with an atom level. So atom level is the dimension or the unit what we use is angstrom, which is not easy thing to do, which is one level below micron and one level below nanometer level. So then when you go smaller and smaller, the design and the manufacturing, everything will become more complex. So that is one of the reasons. And you cannot manufacture semiconductor devices in any place. It has to be highly clean. We call it as a clean room. Hence, again, it incurs more cost. Then they have more technology. You cannot have an open environment, or the equipment cannot run on the atmosphere level. It has to be vacuum, like a high cooling. A lot of other complicated things are there. Right? Then the next one is on the materials. So there are forbidden material, right? So like a rubber or a plastics or copper. So you cannot use some of these materials in the semiconductor area because it reacts with the semiconductor devices. So hence there is a restriction on the material. So you have to pick a handful of material and it comes with its own cost. Right? So I have given a diagram to make you understand. If you see from the left to right, the 1, 2, 3, 4, 5. Fifth one is our human hair. Human hair is the diameter of 100 micron, and we are talking about 0.1 to 0.5 nanometer diameter for an atom. It is much scaled down size, which we cannot even see through our naked eyes. Hence, you have to appreciate how complex the system would be, right? So that's an analogy or picture I have given here. So in short, with all the reasons mentioned, so it has to be high precision if you want to really get a product right. Okay. So that I'll move on to the next slide. So I mentioned about clean room. So I'm going little detail about it. So clean room, why and what is it? So it is basically a space where we control the particles. So what it means, it is a well isolated and controlled environment, and which continuously monitored the number of particles, and hence it is cleaned all the time, right? So clean room is not easy. Every square meter or every square feet incurs a lot of cost. So if you see on the right picture, right, so this is how you have to enter any particle from human body. You have a shirt or you have a dress, any particle gets generated from the human dress, it goes and sits onto the microprocessor fabrication, then that processor won't work. So that is the criticality. So you need to maintain it, and all the manufacturing, all the testing, all the integration can only happen here. You cannot do it in any lab or any room. That is the expectation, and that is the requirement for a semiconductor devices manufacturing and integration. Right. So this is about clean room. There are a lot of classifications. They call it as a class 10, class 100, class 1000, class 10,000. Based on the phase of the manufacturing or testing, there is a trade-off. You can go between these classes, but still it has to be within the clean room environment. Okay. So moving on to the next slide. I'll talk about big picture about the entire chip design, right? I will take an example of, say, Intel Core i7 processor, right? We are using that in our devices, right? Laptop or desktop. If you want to really make that, there is a huge, it's a 500 billion business, right? There are a lot of series of actions happening, right? If I put them down in a three buckets. So one is the circuit design, which I'm showing on the left bottom. So they work on the next generation circuit. How can we increase the speed? How can we reduce the footprint? Right. That is how the core R&D architects come up with a new design. Right. So that is part of circuit design. Then the second one is the verification. So once they have designed, created the architecture, so they make sure it's going to work. So then the third phase is the fabrication or the manufacturing. Now, the design is ready, the idea is there. We need to get them manufactured. That is the smaller portion, fabrication, and a little bit on the packaging. Then the last one is now the physical device is ready. So then we need to have the mechanism of testing them and validating them and making sure it can be delivered to the market. Right? So today, in the interest of time, we are not going to talk about all the things. We will only talk about the highlighted one, fabrication. So in semiconductor, we call it as a fabrication. In other industries, say automotive or aerospace, we call it as a manufacturing. So both fabrication and manufacturing are same. Today, we will do a deep dive onto this, right? Next slide. So again, I don't want to go 30,000 feet. I wanted to start at the 1,000 feet level. So given a basics about a semiconductor. So as a term, we know it is between conductor and an insulator. Right? So conductor, we know all the metals and some of the other materials which conducts the electricity. Same with the insulator, like a glass or plastic or wood. It doesn't conduct. The electricity is called insulator. So the semiconductor can act as an insulator as well as behave like a conductor. When you add some material onto a semiconductor base material. For an example, silicon is a semiconductor material, and you inject some of the foreign material. We call the process as a doping. Then it can act as both an insulator as well as a conductor, right? So that is how a semiconductor term is defined, and that is the specialty of this material, which can be used to manufacture transistors on top of it. Okay, moving on to the next slide. This is again, for college or schools, we have studied the periodic table. I've given an idea where these materials are. They say group 3, 4, 5. I have highlighted some of the materials which are part of semiconductor family. And on the right side picture, again, I've given some of the materials. Basically, it talks about the conductivity and the resistivity. That is how the semiconductor materials have been classified. And silicon, nothing but the sand, is the most abundant material, and this is most popular semiconductor material. So we call them as a substrate. All the devices will be built on the substrate. So it is very easy to get, and it is widely available on the planet Earth. So that is one of the reasons we started using silicon as a semiconductor substrate material. Okay, so I'm not going in detail about the periodic tables, of which you must have all familiar from our school days. Okay, moving on to the next slide. So this is again a quick overview on the transistors. When we say semiconductor and the microprocessor, you open, I've given some picture of an Intel Core i7 for your easy understanding. And also, the size of one of the humans holding it on his hand, on his palm, right? So when you open it, it is all about making a transistors and putting them in a space. For your information, Intel i7 processor, you open it, you may not see it, but it has 3 billion transistors. Right? So it's such a huge number of transistors. When you go back 20 years or 30 years back, they hardly had only in hundreds of transistors. Now, thanks to the technology, they're able to package more and more. So what a transistor does, right? So transistor is like a switch. It can do like on and off. The substrate on the right side picture, the blue color is a silicon or a semiconductor material. On top of that, they're going to connect a source and drain, and they'll put a voltage on it. Then when you pass an voltage, either it can store some data, or it opens up the channel and it transfers the electron from source to drain, right? So that is how when you have series of transistors packed in a smaller place, and when you want to run a mathematical or computation, all it does is it stores one and zeros, and it gives a binary. And the more you have, the quicker response you get on your computer or any devices or your cell phone. So that is how the entire semiconductor devices gets manufactured. So a lot of transistors in a given space, you'll achieve a faster and cheaper products. Okay, moving on to next. So what are the driving factors for a semiconductor devices? Again, I just showed you on the processors, right? So all we are talking is about 4 factors. One is size, speed, power, and cost. So the smaller the size, the faster the device, then the lesser the power consumption, and the cheaper, right? So it is like more of a greedy expectation, but that is what driving this industry fascinating, right? So when the size is small, the electron travels lesser, which means faster the computation would be. Then the increased density, again, you are packaging so much, then it increases the speed. Then the lower power consumption, again, the cheaper it would be. So overall, cheaper, faster, and smaller is what driving, again, as I said. But the question is how smaller the chip can be, right? So we are going smaller and smaller and faster and faster. So what is the end? What is the future? So it is little challenging, but because of the technology, it is still possible to achieve. Okay, I have some more information on the next slide, which talks about Gordon Moore. He's a CEO of Intel. So he had given an idea a couple of decades back. So he's a visionary, right? So he said, every 2 years, the number of transistors would be doubled in the given space. So if you take any microprocessor, right, if you have 10,000 transistors in the same space, after 2 years, it becomes double, and the size also becomes half. So that is the message he has given, and this has been true so far. So every other year, transistors are getting doubled, and speed is getting increased. It is all possible. One is on the circuit design, and second one is on the capital equipments which manufactures these devices. Okay, so moving on to the next slide. I will, since it is basic I'm covering, now I'll go a little faster. So they call it as a node size. This is how people talk about the device in the market. They say, hey, 5 nanometer device, 10 nanometer device, no, not 20 nanometer device. So it is keep on going down and down. One of the main success to make that happen is we call it as a photolithography. This is one of the processes in the semiconductor fabrication. So this makes making this possible. And I've given a note about Samsung processor, 9825 Exynos. Now, this is used in Galaxy Note 10. This is the first one they used using extreme ultraviolet lithography, which use a 7 nanometer node design. So if you see, like 20, 30 years back, the node size was 10 micron, 6 micron. So all the way now we are talking about 5 nanometers and sub 10 nanometers basically, right? So that is how the industry is driving, the technology is proceeding. Okay, moving on to the next slide. Yeah, so now we get into the overall semiconductor fabrication process. Now the design is ready. Now it is all under soft copy. Now we have to get that manufactured. So in manufacturing, there are two processes. I'll go a little faster now. So first one is called the front end process. The second one is the back end. Front end is all about making the silicon ready and printing the circuits on them. Then the back end is, taking the individual diodes, we call it as diodes, and packaging them, testing them, and ship to the market, right? So the circular one is called silicon wafer. Then the middle picture bottom shows about the printed circuits. Each small square would become a microprocessor, maybe a i7 processor or so. Then the last phase is making them cut and package them and ship. So moving on to the next slide, we'll talk about the front end process. So first one is the chip design, which as I mentioned, the architects and the electronics and the electrical people will do a design and come up with a optimum design which is ready to get printed. Then once the circuit is designed, then they'll print that on a piece of glass. Any circuit would be printed on it, which is called reticle. Then this will be used in the photolithography process, and this will be printed on a substrate. Wherever you see substrate, that is nothing but a silicon in the fabrication process. Okay. So this is the first process. Then moving on to the next slide, we'll talk about how they get the base silicon. Now what we do. So all they do is you take the sand and you start melting them. Then it is called ingot, and you put them on a centrifugal system or a machine and make them grow as in a cylindrical phase. Then all you do is grind them and polish them, then slice them, right? It's like a cake. You cut them, and each one, like a multiple sizes, like a 200 millimeter, 300 millimeter, 400 millimeter diameter, and thickness ranges from 0.6 to 1 millimeter thick, like a compact disc, right? So they slice them, and each one is called as a wafer, right? So the entire circuit is built on this wafer, right? So this is the first step. So once the wafer is get manufactured, then the real process starts. Moving on to the next slide. This is all a front end process. So I don't want to go in detail because it's a little complex. I'll give a high level update. So in front end process, all we do is take the wafer and have the deposition done. You have to have oxidation layer, so to avoid some contamination. Then you'll do a deposition of some material, because on top of that you are going to print some circuits, right? So you will do some deposition, and there are various machines to do that. They call it as chemical vapor deposition, physical vapor depositions, and all. So for you to understand, there is a mechanism in which we deposit material on the front end process on top of the silicon wafer. Okay, on the next slide. This is a key process, out of entire semiconductor manufacturing. This consumes 50% of the time, because this is what is going to print the circuits on a wafer, so which is called photolithography. So lithography is anything like a negative and positive, like the way we used to take our photographs a few years back. Okay, so all it does is, so in the circuits will be printed on a reticle, which I mentioned earlier. So this is a reticle. Then you shine a light. Then you put a lens, which basically scales it down, which shines on the photoresist layer on a wafer, right? So when it gets exposed, it gets printed. So it keeps printing on the entire wafer. Each small square is one processor or one device or one diode, right? So in a single 300 millimeter wafer, that is the most common wafer or what we use, you can make hundreds of devices. So this is very complicated. This equipment is very, very expensive, because a lot of optical components, a lot of sensitive, because you have to print and overlay. If there is any misalignment, then the device is a scrap. Right. Moving on to the next slide. I've given some insight on the next slide. I'll talk about the device. Mike, can you move on to the next slide? Mike, are you there? I'm not able to move to the next slide. No, the previous one, please. Previous, yeah, right. Next, yes, stay on it. So I'm giving an analogy, how expensive it is. Again, I have taken some picture from the internet. It is all approximate. So photolithography, as I mentioned, it's a game changer. 50% of the process is done by it. It is one equipment, so it is maybe a size of a bedroom or a conference room. It is more than $100 million. It is as good as you buying an Boeing 747 airplane. So why it is expensive? If you see on the right side picture, it is very, very complicated. Again, high precision is required, because you are going to build multiple layers on top of each other, and when you don't have the accuracy, then you will not get the device as intended. Okay, moving on to next. So now you are ready with that. Then what we are doing is ion implantation, where you add, they call it as an N-type device, P-type device, where all we are doing is adding an impurity or a doping or a foreign particle into a on a silicon wafer, to making it as a semiconductor device the way we want. Okay, so keep in mind, ion implantation is a process. All we do is a doping or adding an impurity to make a P device or a P-type device or N-type device. Okay, moving on to next slide. So now I have skipped a couple of device steps, like a etching and a photoresist. So now the device is manufactured. Now the circuit is printed on a nice wafer. Now the device is manufactured. Then there is a huge the big department, which is inspection and metrology. All they do is they do an inspection and mark wherever the device is defect. If you see here, on all the red dots are like a defective devices, and what they do, they will do a slicing. It is like, again, cutting a cake or cookie. So every small square is one device, right? So say if it is i7, so you can manufacture, if you count maybe 70, 80 i7 devices you can get out of a 300 wafer. So they slice it and cut it, and each square, on the right side picture, you can see each square is taken out, and you are going to assemble them, adding the lugs and adding the connectivities, etc. Right? So this is how each devices will be formed. Okay, moving on to next slide. I have a detailed picture about it. On the next slide. Yeah, so here what you see is now the gray piece is our semiconductor device, then all the golden things are connecting pin. So they do a bonding with a gold wire and lead frame. This is called wire bonding. There is a lot of equipments which does that. Now the device is ready. So then the final testing, I call it as validation and testing. And each device is called maybe a Qualcomm processor or Exynos processor or Intel processor. You name any device in the market, it is as good as this. Then it is packaged and shipped to a customer. The customer is like our end user, which will be consumed on a laptop or on a cell phone or on even a washing machine or airplane, wherever it is, right? So hope you got an decent idea about how the semiconductor devices are getting manufactured. Okay, with that I'll move on to the next step. So I've given an analogy, so now for a software engineer, or a mechanical engineer who just came out of the college and see, how exactly to correlate this on our day-to-day life. So I've given a Vietnam Dong on the right side, on the left side, all the semiconductor processes. So I'm kind of giving an analogy or a comparison for you to understand more. So, if I say silicon, you take the paper, the currency paper is equivalent version of, assume a bare silicon wafer, right? Then the first process, what we did, you wanted to etch it. Etching is a process there. You want to cut them. In the paper, we do equivalent operation as a trimming. Then you have to add an impurity, implanting or deposition. I've given which is equivalent of adding colors and adding some securities, right? Then Ho-Chi-Minh and these numbers and adding the all the information on the right location. It's all designed in the circuit design phase. How big the head size, how big the numbers, how big the flag, all those things are done in the design phase, and it has been transferred into the reticle, which is nothing but the printer. Now the lithography or the printing, what it does is it just prints on the location where it's supposed to get printed, right? Then the quality inspection and metrology, what that equipment or that process does, it makes sure the 500,000 number is on the right location at the right size, right? So right spot at the right size, and it also measures the size. So that is all done by a quality and inspection process. So in overall, if I want to compare a semiconductor fabrication with the making of a currency, this is how it would be. So given this analogy, for a non-semiconductor background person to understand, right? So moving on to the next slide. So we are coming to the end of the presentation. So now there are, I've given into 5 buckets. So now we know it gets manufactured. So what are all the equipments and who are all the players? For a confidentiality, I'm not giving the company names here, but if you Google it, you will get all the information. So there are few players who does ion implanters. There are various types. Then etching and deposition, there are many equipments, various flavors, right? Physical wafer deposition, atomic layer, etching, and so on. And lithography, there are a couple of them, DUV lithography equipments, EUV lithography equipment. So when I say equipments, it is like half of this room size equipments, which manufactures the devices. Right? Then some more equipments, epitaxy, rapid thermal cooling. These are all part of the semiconductor fabrication. Right? Then the last one is one of the important equipments, which is not a process equipment. We call it as a yield management. So it is a very critical to inspect and measure and finding defects on a device, making sure it is good to go. So if you don't say it is good to go, then it is as good as it's a scrap piece. So inspection and metrology is a huge equipment areas as part of this, and it requires a lot of precision again. Okay, moving on to next slide. So if I put them into this, again, I've given a zoomed in detailed view. Each phase has their own equipment. So I have given a smaller picture of the respective equipments. It looks like a rectangle or cuboids or cubes. But when you open the door of this each equipment, you'll see a massive system in it, right? So this equipment is costlier than a Lamborghini or a Ferrari car or equivalent to an airplane, right? So anywhere from 10 million to 100 plus $1 million. The reason is, which is all using optical system, high precision motion system, then robots, wafer handlers, sensitive gas distribution systems, etc. So that is the reason this is all expensive, and these are all the major players in the world, who does equipments on the each process. Right? So if I compare this with automotive, I can say, for painting you have one equipment, for drilling you have one equipment, for cleaning, for engine you have some equipment, right? So same way, on each phase you have their own equipments, and some specialists are there in the world. Okay, moving on to next. Yeah, so what is the technology breakthrough? So what is the future, right? So now from deep ultraviolet, they are getting into the new lower wavelength light, which is called extreme ultraviolet, which is making the devices smaller. And in the inspection, they are adapting, X-rays and E-beams, electron beams, again, which is trying to find the smaller defects. Then on the reticles, they are coming with some cluster-based electron beams. And on top of silicon, they are coming up with an alternate substrates. So they call it as SiC and FEMOR. And they're exploring on using the semiconductors in the newer markets, LEDs and displays and etc. So there are quite a few interesting research is going on these areas, and definitely it is in the right track. Okay. With that, I'll go on to the next slide. We'll talk about, as an engineer, what is the take for me, right? So there are quite a few opportunities in semi equipments with HCL in Vietnam. I've given various subsystems on the picture, which includes mechanical, software, hardware design for any capital equipments design and development, right? So, as I mentioned, robots, automations, firmware, embedded system, cybersecurity, software development, augmented reality, virtual reality, gas delivery, optical frame design, which includes all the complex designs and understandings, right? So this is really in high tech. Okay, moving on to next slide. If I want to pursue, a career in this, what it requires, right? What kind of qualification, education I should have? What kind of areas you'll get exposed? What are all the skill sets you require? So I've given a few data points here. So anybody who has a mechanical or production, electrical, electronics, computer, or IT background, information technology background, can pursue a career in this. And what you learn, right? Software testing, value engineering, new product development, product integration and validation. It's all hands-on exposure. Then skill sets I've given. For mechanical, you'll do a 3D modeling and analysis. Then electrical, you will do a simulation and schematics. Then on the software, you will do a coding, testing, and development. And on the digital space, now we are coming with an AR, VR, MR. So this is all augmented realities and virtual realities. Okay. Moving on to the next slide. So I would like to conclude on the key takeaways and some of the summaries of this last 45 minutes or 50-minute session. So in short, every electronic item you touch has a semiconductor device. So this industry will grow and grow forever, right? And this industry just not follow the same pattern, this device, stay for next 10 years. No, this demands an innovation, continuous innovation all the time. Then only few players in the world who competes with each other. You take a engine, there are many players. Now you take a suspension for an automotive, you have many players, but you take an implanter, only maybe one or two in the world. You take a lithography, maybe one or two in the world. So very few players, which denotes how complex and what kind of people you should have, right? So then now they are all adapting machine learning, artificial intelligence, data analytics, all those newer technology areas. Then you want to continue or pursue, then you need to have little bit of awareness on semiconductor standards, basic understanding on mechanical precision engineering, and also understand some on the domain, and you should have some interest. Okay, I think this is a fascinating area, and you should have some aspiration, whom you want to achieve something on this domain. So otherwise, you really no need to have an expertise on this, because not everybody comes with an experience and expertise, right? But all you have to have is this understanding and the passion to learn and the ability to innovate. Then this is a area to excel and pursue and excel. Okay. With that, I will conclude my presentation, and back to Mai.
Thank you, Mr. Dana, for sharing us your expertise. That was a very insightful presentation. So now let's move on to the Q&A session. As a reminder, you can still submit questions through the comment box. It looks like we have a few questions. So our first question is from 𝗏𝗃𝗺. He asked, why are these semiconductor capital equipment being very expensive? Please.
Okay. Yeah, I think as I mentioned in the previous slides, the moment you add more complications or more precision and more accuracy manufacturing parts, and in the environment in which it gets integrated, like a clean rooms, naturally the cost of the equipment gets added, right? So when you say we are talking about 5-micron movement, 2-micron movement, you have to have a special equipment, right? Like a 5-axis machine or so. Then when you add it, the manufacturing cost goes high naturally. The same way, this is all getting manufactured in the clean room. So when you do it on the workshop or a factory, it takes say $100 per hour. When you move it to a clean room, it goes to like $10,000 per hour, right? So when you sum it up, so it has to be expensive. Otherwise, you cannot achieve the desired output, or you cannot manufacture the desired equipment or device. Okay. Next question.
Yes, thank you. The next question is, why clean room environment required? Is it easy to build a clean room? Please.
Okay, so the question is about the clean room. Okay, so again, if you do it in the regular environment, right, or any factory environment, so you will have particles. Even though you see environment is clean, there are particles. Size ranges from 5 microns to 50 microns, or even 100 microns level, 100 or 200 microns level, and unknowingly those particles will get deposited on the wafer, right? So wafer is all about the circuit is all about flow of electrons. So if the particle goes and gets stuck, then the flow of electron would never happen, and that device would be eventually would be scrapped. So clean room is necessary to make these devices. Okay, next question please.
Yes, thank you. So the next question is going to be, where are the, can you see that? Where are these semiconductor capital equipment companies are located?
Okay, yeah, it's a good question. So, major players are from the US. I can say ion implanters, then optical inspection and metrology, then etching company, deposition and all, and lithography manufacturers are from the Netherlands, and some of the etching and lithography manufacturers are from Japan side. So US, then Japan, US, then Netherlands and Japan are the top players. Now other countries also coming up with their own manufacturing, equipments, design and development. Some of them are in Israel, some of them in China, and it is coming up. Okay, next question.
Next questions. How would be the career growth for a mechanical engineering graduate coming out of college who wants to pursue this career path?
Okay, sure, I can answer because I'm a mechanical engineer. So, so when you come, you will get into the projects where HCL works for our customers on a various processes, which I explained earlier. So when you get in, the primary requirement is you should be familiar with any of the CAD tools like a Creo, Unigraphics NX, or SolidWorks. So then all the design and development happens there. Then once you start understanding the CAD, then you will start growing like a design support. No, we will not be exposed directly on the complex design. So design supports. Then you get into the design of the equipments. Then if you are interested in pursuing on the technical path, then you can become a technical architect, taking some of the areas where you are interested. You are interested in optical, you are interested in cooling, you are interested in vacuum, or you are interested in precision tooling. Now you can pick what is on what you are passionate about, pick the path, and then you pursue. Then you can become a technical architect, and you can become an enterprise architect, and you can move further. Or you want to become a program manager or technical manager, you want to manage the projects, then that is it is a managerial path that is also available. So first you have to develop an expertise, understand the domain, then a career path is set for you. Okay, next question.
Thank you. So today we have a lot of questions. The next question is going to Rajesh Kumar. How to validation done for accuracy? Can anyone validate easily? Please.
Okay, definitely not easy. If it is easy, then the product cost will be only, $1 million or less than $1 million. So the validation, if I say, I'll talk from mechanical side and also software side. So if I talk from mechanical side, you have manufactured a device. So how will you validate? So optical inspection and metrology are a place which can measure up to nowadays angstrom level. So that equipment is using a optical system which gets calibrated at that level of accuracy. And once that accuracy is set, then the semiconductor devices, right, which will be kept on it, then it will measure. So there is no vernier caliper. It is all about light, laser, then a optical system, so which is highly sophisticated, which is capable of validating design requirement versus an actual. Okay, next question. Thank you, Rajesh, for the question.
Yeah. Next question is going to, what are the pros and cons of each these dicing methods like laser, mechanical, plasma dicing, sir?
What are the pros and cons of each dicing methods like laser? Okay, this is a big question. Maybe I will give only a quick glimpse. Maybe I can answer this offline. So etching is all about removing material from a substrate, right? So when you do a laser or mechanical or plasma, right? So it generates heat, right? So and also it deforms material, right? So now there is a thing called dry etch. Wet etch and dry etches are there. So according to me, dry etch has become popular because it does not need any drying. If you put a wet, then you have to put them under oven, or it's like a fan and make them dry. So, but dry etching has more advantage nowadays. But there is some need for wet etch also. So in short, dry etch is widely used now because of its application and ease of use. Then mechanical etching, I'm not sure about it, but laser and plasma is almost same. So it is only a source. Light source is different. So plasma is you generate a source. Laser is already there is a box, and from CO2 you are generating the laser and it's coming it out. So Victor, I can share some of the links where you will find some useful information. Thank you for the question.
We have a lot of questions, but because the time, so maybe you can drop the question at the so you can email us your questions. So Donna, is there anything else you want to cover up before a wrap up?
Yeah, I would like to say thank you, team, for joining on a weekend. And I'm very passionate in semiconductor domain, and I will be able to answer all your questions. So once I get the questions, don't worry, I will share those, post those response back. And I appreciate your time and listening me patiently for last 45, 55 minutes. Thank you, Mai, for facilitating it.
Yeah, great. Thank you, everyone. We appreciate you still being here. One more time, thank you, Donna, for your wonderful presentations. Hope that today's event will bring you useful knowledge. If you have interested in career opportunity at SCL, please visit our website aclvietnam.com and find out available jobs. On behalf of ACL Technology Vietnam and our presenter today, thank you for joining us and have a great weekend. Bye.